Okay, good morning. Welcome back. Happy Friday. Today is our 30th class, and we are covering theorems about differentiable functions. Coming up on Monday, quiz number 4 is going to be assigned, so I will hand it to you Monday. You will do it over the next 2 days and then give it back to me Wednesday, right at the start of class. Also, Monday is going to be our project check-in day, so as usual, you will get the most out of that day if you come in as close to the recommended schedule as possible for our 2 projects. On Wednesday next week, Wednesday is the day before Thanksgiving, but that is a regular day here at GCC, and we will have class. Wednesday next week is a related rates in-class quiz. I'll give you details about that, but I think I've mentioned that's going to be a quiz where you work with each other, the only quiz where you work with each other. So you'll do that in class on Wednesday, and there's no other agenda for Wednesday's class. And then looking ahead, we come back right after Thanksgiving on Monday the 28th, and the data project is due, and then the following class, Rainbow, is due. All right. Questions on the calendar? Okay, then let's take a look at page 25, and see if we can get through the demo here. In this class, we discussed 3 theorems about differentiable functions: the mean value theorem, which is going to be new for us, the increasing function theorem, which is old for us, and the racetrack principle, which is new for us. Some of today will be a bit more theoretical than usual, so you'll be strengthening some new math muscles. A lot of this semester is about calculations, and a lot of today is about theory. So a little bit of a different flavor for today's class. Number 1, the mean value theorem, abbreviated MVT. Let f be a function which is differentiable on some open interval a comma b. There is at least one number c between a and b such that f prime of c equals f of b minus f of a over b minus a. I warned you, today is more theoretical than usual, right? These symbols right here probably don't have a lot of meaning on their own, but with a picture, I think this theorem is going to make a lot of sense. We've got this function here. It just needs to be differentiable. Looks like it is. And we've got a and b are the endpoints, the x values, and then f of a and f of b are the y values. And it talks about this expression right here, f of b minus f of a over b minus a. What can I draw on this picture so that that expression has some meaning? What can I draw? A tangent line? Is that what f of b minus f of a over b minus a is? A what? Which? f of b minus f of a, that's a change in y values, right? And b minus a is a change in x values. So that's a change in y on top of a change in x. What is that? That's a slope, right? Change in y over change in x. The slope of the line connecting which 2 points? B and the A. It's a secant line. So we're going to draw a secant line through those 2 points. Something like that. And my secant line, I'm off my game this morning. All right, that's close enough. Okay, so that right there is the slope of that line is the right-hand side of this expression. The left-hand side of this expression is f prime of c. We know that the derivative is the slope of a tangent line. C is just some point between a and b. So we don't know exactly where c is, but what we're saying is that the slope of the tangent line at this point c is equal to the slope of that secant line. What can you say about 2 lines that have equal slopes? They're parallel. So all this theorem is saying is that there is some tangent line between A and B that is parallel to that secant line. Can you draw it? Can you estimate it? Just sort of eyeball where you think the point is. I'm pretty sure there's only one point in this picture where the tangent line is parallel to that secant line. So for me, it's maybe somewhere around there, which means that this number down here is what we are calling C. Okay? So in English, the mean value theorem says that there is some tangent line that is parallel to the secant line. Starting and ending values are given. typical calculus problem is to find the magical c with the tangent line parallel to that secant line. Let's take a quick look at a sketchpad demonstration here. Okay, in this case, A and B, again, are the endpoints. X is just some generic point here, and it can go any place, left or right, but stops at A and stops at B, okay? And so, again, what secant line am I imagining here? A to B, so we're going to show you the secant line connecting A and B. And in your mind, you are going to take this point and just trace it all the way through and see if you can't find any tangent lines that are parallel to that turquoise secant line. How many tangent lines do you see? 2, right? There's one someplace there-ish, and then another one someplace there-ish. All right, find them. So the first one is up there, and then the second one is there. Cool? So the mean value theorem doesn't say that there's exactly one. It just says there's at least one. There could be 2 or 4 or 50. All right, coming back here. Number 2. 2 zombies, Goethe and Hertz, start a race in the same location. If during the race, Goethe was consistently shambling slower, oh wait, which one? I lost where I was. Yeah, start a race in the same location. If during the race, Goethe was consistently shambling slower than Hertz, what can you conclude? Okay, so let's think about this. They start in the same exact location, and Goethe was slower at every moment in time. So what does that mean about their locations relative to each other? Right, and who's consistent? What is Goethe doing the whole race, winning or losing? Losing, right? Because they start equal, but Goethe is slower the whole time. Okay, so then I'm going to write this like a little bit symbolically here. If we let g of a number represent like where Goethe is, like just imagine the track is the x-axis. So, and if we decide to say, okay, the start, we're just going to call it time 0. So what do we know about g of 0 compared to h of 0? They're equal because they start the race in the same location. And we also know that this thing here, Goethe is slower than Hertz, means that the derivative for, let me write it, is it? Yeah, okay. The derivative for t compared to the derivative for, derivative for g compared to the derivative for h, because if g is the position of Goethe, then g prime is the speed of Goethe, right? We know the derivative of position is speed. So Goethe is slower, so what does that mean here? Less, right? Goethe is slower. Well, I mean, it could be an equalizer. Maybe they're equally running the same speed at some points, but and then the conclusion that you said was that all the time Goethe was losing. And so how do I write that as a symbol? G is always what? Less than h, right? G is always behind. Again, just imagine them running on the x-axis. Yes, thank you. Less than or equal to. Okay, so that's fine. And then on the other side, suppose that these same 2 zombies complete a race and it's a photo finish. But we still have Goethe consistently shambling slower than Hertz, just like before. What does that mean about where Goethe was during the entire race? Winning or losing? Must have been winning the whole time, right? Because we know that they finish at the same time, same spot, but Goethe was running slower the entire time, which means that Goethe must have been winning the entire time in order to have been equal at the finish line. And so same idea as before, but in this case, instead of saying that their starting positions are the same, it's the ending positions are the same. Okay, number 3 puts this all together. It's called the racetrack principle. Suppose that g and h are 2 functions that are differentiable on the open interval AB, and that g prime of x is less than or equal to h prime of x for all x in that interval. That is to say, g is running slower than h. Goethe is running slower than Hertz, same as we just had. If g of a equals h of a, remember this is the starting spot. A is the beginning of this race. They are tied in the beginning. And what must be true about G compared to H the whole time? They're equal in the beginning, but G is always running slower than H. So G is for sure losing the entire time. Tied at the start and G is slower the whole time, G must be losing the whole time. Okay, part 2 says that G of B equals H of B. B is the end of the race. So this is getting tied at the end of the race, but still G is slower all the time. So what does that mean about G is winning the entire race until the tie at the end, okay? Okay, so it's not really clear like what, so like it's like sort of obvious, intuitively obvious, that these statements are true. It's not clear how that helps us in any way, so you're gonna explore how to use the racetrack principle in the activities. I will say that sort of an optional thing here, but if you have like 10 minutes at some point between now and Monday, check out this video. And if you want to save 2 minutes, you can skip the first 2 minutes, that's fine. And see if you can relate the stuff that you see in that YouTube video to the racetrack principle, okay? If you have time, check it out. I think it'll be fun. All right, so the activities on the next page, what I do want to do is change the order of the activity. So can you do the problems in the order that's listed on the board? First 5, then 6, then 1, 2, 7, 3, 4, and finally 8, okay? I will walk around.